Greetings. Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 20. Today we will continue to look at the common emitter stage, which consists of a bipolar transistor and some other components, and see how this amplifier behaves. So I would like to refresh your memory from last time to see where we ended up with the common emitter stage. So last time we looked at the small signal of the PNP transistor, and what we stated here without proof was that the small signal model of this transistor is identical to that of the NPN transistor. So when we draw the small signal equivalent circuit of some complex topology for both NPNs and PNPs, we draw the same structure. Of course, we have to remember that the emitter, for example, could be down here or could be up here. As long as we remember that R pi goes between base and emitter, and GMV pi and RO go between emitter and collector, we are good. All right, then we went back to the concept of amplifier design from early lectures, and we saw that our first attempt was to buy a voltage-dependent current source and let it sense the signal that we would like to amplify, for example, a microphone signal, and then let the current that this device produces flow through a resistor to generate a voltage. So we said that this circuit takes the voltage, converts it to current, then converts the current back to voltage by letting it go through the resistor, and that's how we generate the output voltage, which is hopefully an amplified version of the input. Later on, we decided to replace this abstract device with a bipolar transistor, knowing that the bipolar transistor is also a voltage-dependent current source. So we applied our microphone signal here and put a resistor here, but then we realized that there is no bias current here. So if the microphone signal changes by a few millivolts or tens of millivolts, this device is dead, there is no amplification. Then we placed the microphone signal in series with a battery and then applied the result to the base emitter, hoping that the battery would establish a certain bias current here to give this device proper values for GM, R pi, and RO, because these are all dependent upon upon IC, the collector current. And then we let the current flow, actually over here, we let the current flow through RL, and that was what we thought would be a good amplifier. However, we realized that when we have a bias current flowing through the device, and let's say it's 1 milliamp of current, that current has to come from somewhere. It has to come from a positive voltage, but we don't have a positive voltage here. So we turned this resistor around and connected it to another battery that goes to this common line here. Now, if V1 is large enough, what we see is that the voltage at the collector of the device can be greater than the voltage at the base of the device, to ensure that this base collector junction is reverse biased and we are operating in the forward active region. So this is where we left off, and today we would like to focus on this and analyze it more carefully and see what properties it presents. All right, so let's draw that circuit again here. So basic properties of, we will shorten this to, abbreviate this to CE stage, common emitter stage. And we realize that the circuit looks like this. We have a resistor connected to the collector, and then to the base we have connected our microphone, a bias voltage, which we call V0, and then the battery is connected here, the other battery, V1, and that's how we ensure that the device is biased correctly. Now, because we have applied V0 to the base emitter junction, it's forward biased, and it carries a current. And because the collector base emitter junction is reverse biased, the emitter current all goes to the collector and is absorbed and comes through RC and goes to the battery, the electrons at least. So what we expect is that there's a bias current here, IC0, maybe as an example 1 milliamp. We have a collector resistor, let's say as an example 1 kilo ohm. And for example, for this one we choose 2.5 volts. And then for V0 we choose 0.8 volts. All right, so we have biased up the circuit. We have a bias here to give us the proper base emitter voltage and proper collector current. We have another bias here to make sure that even though there's a drop across RC, the collector is still at least equal to base, maybe higher. All right, so the first question that we need to answer is, where is the output voltage of the circuit? Presumably, this is the input. So we have V in coming from the microphone between these two terminals. And we said last time that the bipolar transistor converts a voltage at the input to a current in the collector. So we say a V to I conversion. And then this resistor converts the current to a voltage. And that's I to V conversion. So naturally, we might decide that the output voltage is the voltage across this resistor. Sure, we can do that. So let's try to bring this out here. And we say V out is right here, V out. Between this terminal, between this wire and this wire, right? So we can call that V out. Okay, so let's go ahead and just plot these in time as a function of time. Let's say the input is a sinusoid of some sort, so maybe a millivolt or something in amplitude. And then we'd like to plot V out. And in doing so, we actually want to plot everything that we observe here, not just the changes in the output voltage. So for that, I would use an uppercase notation for V in and V out, because uppercase means everything, the bias and the signal change, etc. Let's start with the input. At this point, with respect to this point, what can we measure? Well, here's what we have. As a function of time, V in the absence of a signal, we have a bias voltage of 0.8 volts. So here's our bias voltage, 0.8 volts. And now we have a signal coming in. A signal from the microphone, let's say 1 millivolt peak. So here's the signal going like this. That's the input signal, 1 millivolt peak, 2 millivolts peak to peak. All right, how about this voltage? So let's look at that very carefully and see what we get. So again, I use uppercase V out to indicate that I'm plotting everything that we have there. In the absence of signals, what is V out? Well, we have a constant current of 1 milliamp flowing through RC. So there's a voltage drop of 1 volt from here to here. The current is going this way. The voltage would be positive here, negative here, according to Ohm's law. So we have 1 volt of drop from here to here. So that is the bias voltage that you have, if you want to call it that. So 1 volt. Now a signal comes in. The signal. As the signal goes up and down, this current goes up and down, this voltage changes. So we'll have hopefully an amplified version of this voltage over here, right? Okay, so that amplified voltage would be maybe a little bigger. So we would have an amplified voltage like so. All right, so far so good. But in practice, we prefer to call some other voltage the output voltage. not this voltage here. And the reason for that will become clearer later. But at this point, I will just say it to you and show you how we do that. So let me change the color of my pen and show you where we would like to pick the output voltage. So the output voltage, we will measure it from here to here, not from here to here. Okay? So we will call this V out. And just to make sure that there's no confusion between this V out and this V out, I will call this V out 1. Here's V out 1, and that's what we saw. This is just V out. So again, let's plot this voltage, including everything, DC, AC, etc., to see what it looks like. So here's that V out. So this V out is the following. Again, no signal. If you have no signal, what happens here? Well, we have 1 milliamp of current coming down through this resistor. How do I find this voltage? This voltage happens to be the collector emitter voltage, right? Okay, how do I find that voltage? KVL is our friend. We say this voltage must be equal to this voltage plus this voltage. And it is this one that I'm looking for. So this voltage is equal to this voltage, 2.5 volts, minus this voltage, which is 1 volt, 1 milliamp through 1K. So the voltage from here to here, in the absence of a signal, is equal to 2.5 minus 1, 1.5 volts. So this voltage will be 1.5 volts. And let me write the equation for this because we will see this many times in the future. So V out is equal to this voltage. Is equal to this voltage, which we call V1 for now, minus this voltage. And this voltage is equal to RC times the current through it. So minus RC times IC. This is an important equation to remember for the future. All right. Now, when the signal comes in, what happens? Well, this point goes up and down, just like before. So this will go up and down, and now, this time I have to be careful with the polarities. So this will go like this. So you see that if I consider this V out to be the output, there is indeed a negative sign as we go from the input to the output. Remember the gain was minus GM, remember that the gain of the original amplifier was minus KRL, right? There was a negative sign here. If you consider this V out, then there's no inversion. But again, we're not concerned about this. We forget about this. From now on, we focus on this. The details of this will become clearer as we derive equations for the gain and everything else. But for now, I just want you to remember that the input voltage has the microphone signal riding on a 0.8 volt bias, and the output voltage has the amplified microphone signal riding on a 1.5 volt level bias voltage. All right, so that's what we have at this point. Okay, so from now on we will call this the input signal, this one the output signal, and we perform our calculations accordingly. All right, so let's make some simplifications. In practice, when we are analyzing circuits, we don't want to draw all of these things all the time, especially when the circuit becomes more complex. So we will have some conventions in how we represent different devices and voltages, etc. So here's the simplified view. Let me change the color of my pen and we'll see what this means. So simplified diagram. So these are some conventions that you need to learn because from now on our circuits will be drawn in the simplified form. Okay, so we draw the basic circuits still as before. So here's the basic circuit. No change there. This resistor, for example, may be called RC. This transistor may have a name like Q1 if you want. That's it, okay? No problem there. Now, this terminal is connected to this terminal by a battery. We will not draw this battery anymore. We will put a thick line up here, and we will call it V1. And what that means is there is a battery from here to this common line. Okay, that's what it means, this thick line and this V1. So anytime we draw that, in your mind, you can place a battery between here and this common line. If you remember from basic circuit theory, we often picked a common reference point and called it the ground. So here we will do the same thing. So we will call this entire wire here ground. And the symbol for ground is like this. All right, so I have the emitter of the device going to ground, and I don't need to draw a big line here, so I'll just draw the ground symbol here. I have this voltage source and this battery going to ground, so I draw, for example, the microphone or a representation of this voltage source and the battery going to ground, and this is V0, and that's the microphone. So this should not be strange or confusing. All this means is that these are just connected to each other by a wire. That's all. We just don't want to draw the wire because it clutters up the circuit diagram. All right. Now for the output, remember that the output voltage is from here to here. That's our definition of the output voltage. This point is ground. So the output voltage is measured with respect to the ground. Now, for that, I may just do this. V out. This is very confusing because a voltage is always measured between 2 points. We cannot say this point has a voltage. We can say this point has a voltage of 5 volts with respect to this point. So when I do this, what do I mean? By this I mean this node has a voltage of V out with respect to ground. We didn't draw the ground, but we know that it's there, just the way we had it from here to here, V out. So this is the simplified circuit of that. From now on, we will be drawing it like this. So it's very important that you remember these things. One more change in notation. So let me change the color of my pen to emphasize these so that you can keep track of them. Oftentimes, we don't call this V1 anymore. This is sort of our power supply. So we will change this to VCC. CC evidently comes from collector, meaning that this is a battery that eventually feeds the collector. But it doesn't matter. That's our name, VCC. So VCC is the supply line up here that really is connected to a battery, like what we saw before. Okay, so this is the circuit. Keep in mind that what I have drawn here consists of both the bias quantities, like this guy and this guy, and the small signal quantities, like this guy, right? So if you want to analyze the circuit, we have to separate it into one for bias calculations without the microphone, and one for small signal calculations without this and without that. So we will do these one by one. Okay, so that is our basic common emitter topology. And now we are ready to calculate its voltage gain. Last time we said that one important property of an amplifier is its voltage gain, meaning if I give it a 1 millivolt swing at the input, how much swing do I get at the output? The ratio of the output swing and the input swing will be the voltage gain. So we need to calculate the voltage gain of the common emitter amplifier. This is a small signal calculation because the incoming signal perturbs the bias. We have a bias created by these, we have a bias created by the batteries, and then the signals are just perturbing these bias conditions. So we need to draw the small signal equivalent circuit of this amplifier before we attempt the calculation. All right, so let's go ahead and calculate the small signal voltage gain. Sometimes we just say voltage gain, even though we know it's the small signal voltage gain. All right, so small signal voltage gain calculation. And for that, we will have to draw the small signal model. Maybe we can start with the transistor. We know what the small signal model looks like, as we saw before. It has GMV pi as the main component. That's the operation of the transistor. It's a voltage-dependent current source. Then it has R pi to account for the base current variation with the signal. And then it has RO to account for the collector current variation when the collector-emitter voltage changes. Now, in this calculation, for now, we will assume that the early effect is negligible. If early effect is negligible, the early voltage is infinite, and RO is also infinite. So we will take RO out of the picture. So for now, we assume early voltage is infinite. And that just means that the early effect is negligible. In other words, the collector current does not depend on the collector-emitter voltage. All right, so we just draw that topology without RO. Here's the basic small signal model of the transistor. And this current source is GMV pi. And now we attach everything else. We see that the emitter goes to ground. So that's just the ground. The base goes to a voltage source representing the microphone. So here's a voltage source, which we call Vin. And then we have a bias voltage. Remember that when we draw the small signal model, the bias voltages, all the constant voltages, become zero because they don't change. The small signal model represents changes. These voltages don't change, so their change is zero, so they are zero. So that is replaced by a zero, and we go to ground. Now we go to the collector. We have a resistor, RC. So RC. And then what happens to this guy here? Well, if we are confused here, we go back to the previous version. We have a battery between the top terminal of RC and ground. The battery becomes a short circuit because its voltage doesn't change with time. So that becomes a short circuit to ground. And this is the model of the circuit. We know where Vin is. Where is V out? V out is measured between the collector and ground. So V out is here. This is V out. I don't have room for it, so I'll just write it down here. Again, V out is really measured from the collector, from this point with respect to ground. But we just write it up there knowing that that's the case. All right, our job is to solve the circuit. Very simple. Well, what's the unknown? The unknown is V out. We want to find V out in terms of Vin. And we know everything else. We know GM, we know R pi, we know RC. V pi is not known, and hopefully it will drop out of the equations as we solve the circuit. So you can use any of the techniques that you have learned in basic circuit theory to analyze the circuit. You can write node equations, mesh equations, KVLs, KCLs, etc. Now, as I said before, it's always good to take a step back, look at the circuit for a minute before we jump in and write equations. For example, here, what I can observe is that Vin appears between this wire and ground. And V pi appears between the same wire and ground. So V pi happens to be equal to Vin. So that's good. V pi is equal to Vin, which means that this current source is also equal to GM V pi is equal to GM Vin. All right, so far so good. Now, at this node, I can write a KCL. There are only two currents flowing through this node. One is GMV pi, and one is that current, and nothing else. This wire doesn't carry any current because it doesn't go anywhere. Okay, so here we have to be very careful. A current is flowing out of this node this way. So we'll just call it GMV pi, which is GMV in. GMV in. Now, this current flowing out plus this current flowing out must be 0. The question is, how much is this current? Now you have to twist your mind around a little to see how much the current is. Well, V out appears from this node to ground. So positive here, negative here. And the voltage that would give us this current would be the voltage from here to here, from here to ground, which is actually the same thing as V out, from here to ground. So we can see that this RC, I can draw it like this, you see. I'll just draw this part. Here's V out. And RC starts from here and goes to ground. So I'll just draw it like this, right? Why don't I have to twist it around? Now you can see that this voltage with respect to ground is the same voltage as across RC, which means this current is just equal to V out over RC. And that means that I can add this current and set the result to 0. So that's equal to minus V out over RC, which means V out over V in is equal to minus GM RC. And this is the voltage gain of a simple common emitter amplifier. It doesn't have a units because it's voltage divided by voltage. It's dimensionless. This is a very simple and beautiful equation. It tells us everything we need to know about this simple amplifier that we have constructed. Okay, so GM is the transconductance of the device. And now we realize why that very first circuit that we built using the amplifier bipolar transistor failed. This circuit here, remember, we connected our microphone directly to it, and we were hoping to have gain. Well, because we had no bias, no collector current, GM was 0. If GM is 0, the voltage gain is 0. So the transistor is dead. We get nothing at the output. And this equation exactly tells us the same thing. All right, that is the voltage gain of the simple common emitter amplifier, provided that we have neglected early effect. A little while later, we will consider that. But for now, that's what we have. All right, so one terminology that I would like to emphasize is the following. When we went from this circuit to this circuit, this simplified circuit, we said this is ground, and the emitter is connected to ground. The bottom of this battery is connected to ground, and the bottom of this battery is also connected to ground. Now, when we drew the small signal model, something else happened. The emitter still goes to ground, no problem. But the top terminal of RC, which used to be connected to the battery V1, is now connected to ground. So this ground and this ground have different origins. This ground was hardwired, so to speak, from the beginning. The emitter happened to be connected to the bottom wire, to this wire, and we call it ground, and that was ground. But this ground came about for a different reason. This ground came about because we set the voltage V1, that voltage source, that VCC or V1, to 0, because its value doesn't change. Now, as far as this model is concerned, this is a ground, this is a ground, they're equally good, they're all equated equal, no problem. But sometimes, just to distinguish things, we might call this an AC ground. So these are all AC grounds in this topology. So let me write that here so that we remember it. Sometimes we use the term AC ground just to emphasize that this was not originally ground, but as a result of going to the small signal model, it became an AC ground. Okay? So in a small signal model, we have only grounds, and they're all AC grounds, but some of them came from different places, right? So this is still AC ground, this is also AC ground, except that these grounds, this ground originally was a ground, as you can see here, but that ground was not. Similarly here, this is also an AC ground because originally the bottom terminal of the microphone was not connected to ground. But because this battery was forced to go to zero, we ended up with a ground here as well. Okay, it's good to verbalize this equation. Verbalize meaning write it in words. So here's what we'll do. We'll say that the voltage gain of a common emitter stage is equal to minus GM times GM, transconductance of the device, times the total resistance tied between the collector and AC ground. That's relatively obvious, right? The total resistance tied between the collector and AC ground. Any ground. AC, DC, whatever, it doesn't matter. Any ground. So in this case, it's just RC. You can see that start from here. You go up, you see RC to ground. There's no other resistance anywhere. So that's just RC. And that's the resistance. It looks rather obvious, but later on you will see that you can be confused about it. So if I call this R5 instead of RC, same thing, R5 is the total resistance that appears between the collector and the AC ground, and it will go in here. So whatever we call that, it goes into this equation. So just remember that, and this becomes useful later. All right, so these are simple views of the basic common emitter stage. Now, I would like to go back and re-examine this example and see how much gain we have and generally what kind of conditions we have. So let's go back to that example and see. Okay. All right, how much gain does this circuit have? Well, all I need to do is find the GM of this device, find RC, multiply by -1, that's the voltage gain. So this example incorporates this circuit with the values that I have shown here. So we say for the previous circuit, what we have is GM is equal to IC over VT. So 1 milliamp divided by 26 millivolts. And we'll just write this as 1 over 26 ohms. Very simple. And what else? Well, I just need GM, and I need to multiply it by RC. And of course, RC is 1 kilo ohm. So that means that AV is equal to minus 1,000 divided by 26, and that's approximately equal to minus 38. So oftentimes we just say the voltage gain of this common emitter stage is 38. We don't bother with the negative sign, knowing that there is a negative sign. We just say the gain is 38. All right, so the voltage gain of the common emitter stage with a bias current of 1 milliamp and a collector resistor of 1 kilo ohm is minus 38. Okay, so far so good. Now let's go ahead and redraw these waveforms now that we know how much gain we have. So here's what we will do. We'll start with the input. So let me try to draw these very carefully here. So actually, let me draw these on this side. So let's start from here. We have V in with a bias value of 0.8 volts. And I'm assuming that the microphone signal has a peak amplitude of 1 millivolt. So peak, meaning right here, this peak is 1 millivolt. All right, so this goes to the amplifier. And out comes V out. Now again, this is the entire V out. And the way we think about it is without a signal, we just have the bias values. So remember that V out without the signal is 1.5 volts. So just keep that there. We have 1.5 volts. And then we have a gain of minus 38. So this amplitude will go up by a factor of 38. And then the entire signal is flipped upside down because there is a negative sign. So what we will see is something like this is flipped, and this amplitude is now 38 millivolts. Okay, so that's simple enough. We understand everything about this example. All right, good. Now, let's ask the following question. Suppose you designed this amplifier, you chose a current of 1 milliamp and you got this much gain, and your boss came and said, actually, I need to double the gain. I need a gain twice as much. 38 is not enough. So then what do we do? Well, we say, well, why don't we just increase RC by a factor of 2, right? That will double the gain. So let's go ahead and do that. So I'll change the color of my pen and see what happens. It's always good to explore these ideas. As I said before, the circuit doesn't bite. You can do anything you want and see what the result looks like. It's always educational to attempt these things. All right, so we'll write here, need to double the gain. Perhaps because the application needs more gain, so your boss came back and said, we need to double the gain. So we said, all right, should we double the GM? Should we double RC? Oh, maybe we'll just double RC, not GM, just as an example. So RC goes to 2RC, right? We double it. Okay, so this simple derivation here tells me that the gain will be minus 76, not minus 38, if RC is 2 kilo ohms, right? Okay, but is that really true? Is everything good? Anytime we make a change to a circuit, for example, an amplifier, we have to check the bias conditions. Is the transistor still healthy? Is it in forward active region or not? So we can't just go and double the resistor without looking at what's going on in the transistor itself. Okay, so let's go ahead and plot V out now and see if everything is good. So now we say RC is equal to 2 kilo ohms. Remember that we haven't changed anything else, so presumably IC is still 1 milliamp. And this voltage, VCC, is 2.5 volts. Okay, so let's try to plot V out. The input hasn't changed. The microphone and the bias voltage for the base emitter are still the same. All we did was change the collector resistor from 1 kilo ohm to 2 kilo ohms. All right. So what we are hoping is that this signal swing now is 76 millivolts instead of 38 millivolts. But before we go there, we should ask about this 1.5 volts. Is this still 1.5 volts? Where did it come from? 1.5 volts came from this equation. We said this voltage, 2.5 volts, minus this voltage, drop, gives us the collector emitter voltage, which is V out in our case. Well, V1 is 2.5 volts. Good. IC is 1 milliamp. That's what we are hoping. RC is 2 kilo ohms, not 1. So how much is V out? 2.5 minus 2. So V out without any signal is 0.5 volts, not 1.5 volts. So this is equal to 0.5 volts. Is that a problem? That's a problem, because if the collector emitter voltage, even without the signal, is 0.5 volts, and the base emitter voltage is 0.8 volts, then the collector voltage is less than the base voltage, which means the base collector is forward biased, and we are no longer in the forward active region. The transistor has entered saturation. So we say transistor is in saturation. So now the signal comes in and we have these large fluctuations. So we'll have things like this, and the situation is even worse because over here we are even less than 0.5 volts. So the device is deeper in saturation, we are in trouble. So that's an interesting observation. It tells us that we can't just go ahead and increase RC to increase the voltage gain. Eventually, as RC becomes larger and larger, we don't have any more DC available for the collector. Right? When we started out with a 1 kilo ohm resistor here, we had 1.5 volts available. As RC increases, this voltage shrinks. And eventually, we don't have enough room. We don't have enough headroom for collector emitter voltage to be at least equal to base emitter voltage. So we say the headroom is limited. The voltage headroom is limited. Headroom means how much room you have above your head, meaning how much room we have here, how much margin do we have here before the transistor enters saturation. Okay, so this is a basic limitation of the gain that we can obtain from a simple common emitter stage. We see that as RC increases, even though this equation says we're good, the small signal model says we're good, when we look at the actual behavior, we see that we're not good. The transistor is going to saturation. All right. Now, let's go ahead and write this equation in a slightly different form to answer a second question. I just said that to double the gain, I double RC. You could say, all right, so that's no good. Why don't we double GM? Right? Is that a possibility? So let's try that. Okay, so we go and insert a new page. Let's try to double GM instead. So instead of doubling RC, we double GM. Okay, so this is what we have. AV is equal to minus GM times RC. And we know that GM is given by the collector bias current divided by VT. So we have minus IC over VT times RC. And we concluded that if we just go ahead and double RC to double our gain, something bad happens. The collector voltage, the collector bias voltage, without any signals, falls so much the device goes into saturation. Okay, so to double GM, what can I do? I have to double IC. There's no other way. So double IC. The question is this better? So let's return to the previous page and see what happens if we double IC. All right, so instead of doubling the resistor and ending up there, I will double IC. Okay, so let's go back here. We said V out, for example, without any signals, is equal to V1, this battery here, minus this drop. So we keep RC at 1 kilo ohm, but we go from 1 milliamp to 2 milliamps. Does the situation get better than what we had there? No, not really, because this is a product. Whether we double RC or double IC, this doubles. If this doubles from 1 volt to 2 volts, this result will be 0.5 volts regardless. So in this case, still, we end up with the same situation. So, so ICRC doubles, which means VCE is equal to 0.5 volts, and we have the same problem as before. So let me drink a little bit of water here. Okay, so this is the situation. In other words, ultimately, it's ICRC that determines the voltage gain that we can achieve. So I have a little cough here again. All right, so this is an important limitation. It tells us that so long as we have some bound on this ICRC, we are stuck with a certain amount of gain. We can't exceed that gain. And it doesn't matter whether we want to increase the collector current or the collector resistor. Very good. Let's go on to the next important concept, and that is inclusion of early effect. All right, so we would like to do the calculation of the gain again, but this time use include the early effect. So just to refresh your memory, let's go back here and see what happened. We drew the small signal model like this, but the transistor model did not include RO, which represents early effect for small signal calculations. So it's simple. We redraw the circuit, but this time we attach RO from collector to emitter. And we have to do the calculations again, or maybe not. So let's see how that works. Okay, so I will draw the small signal model of the circuit. So here's V in, going to ground, R pi, going to ground. It has a voltage of V pi. Then we have GM V pi. Then we have RO. These are all going to ground because the emitter of the device happens to be grounded in this example. That need not be the case all the time, but it just happens to be here. And then, of course, our collector resistor, RC, and then V out. So we still would like to find V out over V in. All right, now, do I need to write those equations again? No. I remember how I verbalized the gain calculation. I said the gain of this simple common emitter stage is equal to minus GM times the total resistance seen between, tied between collector and AC ground. All right, so we just need to find the total resistance that appears between the collector and ground in the small signal model. Okay, so we sit at the collector. Here's the collector wire, and we try to find any and all resistances that go from here to ground. What do we see? We see RC as before, but we also see RO exactly in parallel with RC. So I can just put these in a box and call it something, call it R equivalent, right? So the total resistance that appears between the collector and ground, AC ground, is R equivalent, which is equal to RO in parallel with RC. So this is just RO in parallel with RC. That's all. We don't need to write the equations again, because that verbalization of the equation allows us to use it repeatedly and for different types of circuits. So what does early effect do? It reduces the gain, right? Previously we had minus GMRC, but now because we have a resistor in parallel with RC, the net result is lower, the voltage gain is lower. So unfortunately, that is the problem. When we include early effect, the gain is lower. So now you might ask, when do I include early effect? When do I not include early effect? Well, that comes with experience. We can do a quick calculation in our head to see if these two are comparable. If RO is, for example, 10 times RC or higher, its effect might be negligible. We can just say RC. But if not, then we have to include it. And sometimes you are told in your exams and homeworks whether to include it or not include it. Okay, so let's look at an example of how this early effect comes into the picture. So I would like to show you another common emitter stage. So here's a common emitter stage with an input signal. So maybe you can call the microphone again, and a bias. So this is V0. And we have VCC up here. VCC, remember that's just a battery that goes from here to here. The output voltage is here. V out. But instead of a resistor, I decide to use an ideal constant current source. So here's an ideal constant current source. This is ideal and is constant. Constant meaning its value doesn't change with time. It's, for example, 1 milliampere at all times. Okay, so I would like to find the voltage gain of this common emitter stage. How do I do that? Small signal model, maybe, right? So let's do that and see. After we do this a few times, maybe we don't even have to draw the small signal model because we become so proficient with this equation that we can quickly write it. But for now, just to be able to visualize what's happening here, we will draw the equivalent small signal model. All right, so as usual, we model the microphone by an AC voltage source, V in. This battery doesn't change with time, it's shorted out. We draw the small signal model of the transistor, R pi, sustaining a voltage of V pi. Then we have GM V pi. Then we have RO. And all of these are going to AC ground. And now we have to figure out what to do with this current source. Well, we said that the small signal model, the small signal equivalent circuit, represents quantities that change with time. If a quantity does not change with time, it is replaced with 0 because it changes 0. A voltage source that becomes 0 is a short circuit, is a wire. A current source, an ideal current source, which is constant and doesn't change with time, when we want to replace it with 0, we have to replace it with an open circuit. Open circuit meaning incapable of carrying any current. So there will be an open circuit here as the small signal model of a constant current source. And then from here, where do we go? Well, this is VCC, constant voltage, goes to ground. So that goes all the way back to ground. And to avoid confusion here, we just erase this line. So we have RO, and then this goes back to ground. And V out is right here. This is V out. Okay. So again, before writing equations, we just take a look and see what this tells us. Can we simplify it? What's the significance of this open circuit here? Nothing, it's gone. It doesn't do anything, it doesn't draw any current. So we can just forget about this piece of wire here. If you forget about that piece of wire, what we have is just this nice little circuit. And this nice little circuit has a simple gain equation. The gain of that circuit is given by minus GM times the total resistance connected between the collector and AC ground, which happens to be RO. So we see that AV is equal to minus GM times RO. Is it possible to neglect the early effect in this example? Well, if I neglect early effect, RO goes to infinity. So I go to my boss and say this circuit will give you infinite gain. And my boss will laugh at me because I have made a very poor approximation. So in this case, obviously, we have to include the early effect. All right, now, did I really have to draw this model here? Could I just start from this equation? Well, I could have thought of it like this. I could have said an ideal current source becomes an open circuit. So the difference between this topology and the previous topology is that now RC has become an open circuit for small signal analysis. The current source for small signal analysis becomes an open circuit. We don't have RC anymore, right? RC disappeared. So I can just go in here and replace RC with an open circuit, meaning with infinity. And that will give me the same result. So it's not surprising that these two would agree. All right, this minus GMRO has a particular significance for us because it is fundamentally a property of this transistor when you buy it. Once you buy this transistor, there's so much minus GMRO you can get. You cannot get more than that, regardless of what we do around it. Why? Well, here's what we can do. GM is equal to bias current divided by VT. RO is equal to the early voltage divided by the bias current. So it's equal to minus VA over VT. VA is the early voltage, a property of this transistor when you buy it. VT is 26 millivolts at room temperature. This ratio is given for a given transistor. It's independent of the bias current. So that represents a fundamental limit as to how much gain one transistor can provide. One transistor cannot provide more gain than this. So we call, this has a particular name, so we call GMRO, we call it the intrinsic gain of the transistor. because this is the best we can do. This is the highest gain we can get with a single transistor after we bought it, after we know its properties. You see that this gain does not even depend on beta. It just depends on the early voltage. All right. That's a simple example of a common emitter stage. And our time is up. We did not get a chance to talk about input and output impedances, so we will talk about those in the next lecture. I will see you next time.